Camera link is a registered trademark of the AIA.
Transmission protocol.
Camera link uses 1 to 3 channel link transceiver chips with 4 links at 7 serial bits each. At a minimum, camera link uses 28 bits to represent up to 24 bits of pixel data and 3 bits for video sync signals, leaving 1 spare bit. The video sync bits are data valid, frame valid, and line valid. The data are serialized 7-1, and the 4 data streams and a dedicated clock are driven over 5 LVDS pairs. The receiver accepts the 4 LVDS data streams and LVDS clock, and then drives the 28 bits and a clock to the board. The camera link standard calls for these 28 bits to be transmitted over 4 serialized differential pairs with a serialization factor of 7. The parallel data clock is transmitted with the data. Typically, a 7x clock must be generated by a PLL or SERTS block in order to transmit or receive the serialized video. To deserialize the data, a shift register and counter may be employed. The shift register catches each of the serialized bits, one at a time, then registers the data out into the parallel clock domain, once the data counter has reached its terminal value.
Variants.
Camera link comes in several variants which differ in the amount of data that can be transferred. Some of them require 2 cables for transmission. The base camera link configuration carries signals over a single connector cable. The cable used is a MDR, mini D-ribbon 26-pin male plug connector, optimized by 3N for the LVDS signal. In addition to the 5 LVDS pairs transmitting the serialized video data, 24 bits of data and 4 framing enable signals, the connector also carries 4 LVDS discrete control signals and 2 LVDS asynchronous serial communication channels for communicating with the camera. At the maximum chipset operating frequency, 85 MHz, the base configuration yields a video data throughput of 2.04 Gbps, 255 MB per second. The camera link specification includes higher bandwidth configurations that provide additional video data paths over a second connector cable. The medium configuration doubles the video bandwidth, adding an additional 24 bits of data and the same 4 framing enable signals present in the base configuration. This yields a 48-bit wide video data path capable of throughput up to 4.08 Gbps. 510 MB per second. The full configuration adds another 16 bits to the data path, resulting in a 64-bit wide video path that can carry 5.44 Gbps, 680 MB per second. Some camera and data acquisition hardware manufacturers have extended the bandwidth of the interface beyond the limits imposed by the camera link interface specification. These formats extend the width of the full configuration by reassigning some of the redundant framing enable signals to produce a data path width of up to 80 bits over 2 connectors cables, which further increases the video bandwidth. The 80-bit video path can carry 6.8 Gbps, 850 MB per second.
Signal timing.
The image below shows the relative signal timing of the clock and one data line of one of the channel link transceivers used for camera link transmissions. Data words start in the middle of the high phase of the clock, and the most significant bit is transmitted first.
Bit assignments.
The bits of pixel values are not assigned to serial transmitters in order, but are permutated in a complicated way, as shown in the following very busy figure. The upper half of this figure is only relevant for the medium and full configurations which require 2 physical interfaces and 2 cables. The 2 rectangles in the middle represent the cables, with the connector pins of each signal printed at either side. To the left of the transceivers, the list of pixel data bits transmitted over that channel link is printed, from LSB to MSB. The characters L, F and D refer to the line sync, frame sync and data valid bits, respectively. The underscore represents an unused spare bit. It remains to be said how pixel data bits are assigned to the bits 0 to 71 used in the figure. For grayscale pixels, this is a trivial 1-to-1 mapping. For color pixels with a multiple of 8 bits per color, the colors are simply concatenated in the order red, green and blue, from LSB to MSB. For 12-bit RGB data, the lower 8 bits of each color are assigned to data bits 0 to 7, 16 to 23, 32 to 39. The higher 4 bits of each color to bits 8 to 11, 12 to 15, 40 to 43.
Cables and connectors.
The standard prescribes 26-pin miniature delta ribbon connectors, MDR26, for use with camera link. The shrunk variant SDR26 is allowed since standard version 1.2. The connector pin assignments are shown in the large figure in the previous section. The connector pinout is the following. Matching differential pairs are deliberately located at opposite sides of the connector, and at different connector sides at the different ends of the cable. This prevents skew due to the connector being mounted perpendicularly on a PCB. Camera link cables are shielded twisted pair cables. The standard specifies that differential pairs must be individually shielded, and the cable as a whole must have 2 shields. Some companies save costs by not shielding the 2 serial interface signal pairs, which carry slower signals than the camera data. These cables have 1 camera end and 1 grabber end and may not be reversed, and cannot be used as a second cable in a medium or full configuration.
Interface standard specifications.
The camera link standard is maintained by the AIA. The introduction of the camera link interface standard 1.0 was released in October 2000. Revision 1.1 was adopted in January 2004, with expanded software function support. The Standard Committee adopted version 1.2 in January 2007, introducing many SDR, shrunk D-ribbon connectors, SDR26, and Power over Camera Link, POCL. Annex D of Revision 1.2 adds mechanical and electrical descriptions to the standard, especially cable performance. Annex E of Revision 1.2 lists requirements of POCL equipment. Camera Link 2.0 was released in November 2011.